All right, so this lecture is on the subject of climate and radiation. Again, my focus is rocky planets mainly. So what I'm going to talk about, here's the outline, some basic climate physics. So I'll start with some simple climate thought experiments. Then I'll talk about some molecular issues of radiation, absorption and emission. And then finally I'll talk about climate stability, so long-term feedbacks that maintain a stable and habitable climate on the Earth, and then also a particular case when things go wrong, which is the worst case of instability probably, which is a runaway greenhouse, which illustrates some of the issues of radiation that I'll talk about earlier. So, first of all then, some basic climate physics. Why do we care? We care for Earth-like exoplanets basically because of the issue of habitability, which conventionally defined means liquid water on its surface, so having a temperature and pressure regime where that's possible. And of course, this defines the habitable zone around other stars. So to gain insight into climate, let's consider some simple thought experiments. We'll start with the basics. The emission temperature of a planet, and something which you may not have come across, but the skin temperature of an optically thin upper atmosphere. I'm assuming everybody is familiar with black bodies for the sun and say for the Earth, and for the emission of the Earth being about peaked at 10 microns in the visible. For solar, this is scaled by a factor. Basically the effective temperature of the Earth here is 255 Kelvin, which is equivalent to the basically bouncing solar radiation without going thermal infrared. And these black body curves, if you calculate the total flux, it's just the Stefan-Boltzmann law for a black body. So that's where we start. And an atmospheric skin temperature is, so imagine your planet then has to radiate at an effective temperature for the Earth, that's 255 Kelvin. It doesn't do that from the surface because the surface temperature of the Earth is about 15 degrees Celsius on average. So instead it does it from some average level higher in the atmosphere where photons, the infrared photons, are escaping effectively. And a sort of average altitude, of course it depends on wavelength, but roughly speaking, you could think of these photons as escaping about 5 kilometers altitude from the Earth's atmosphere. A sort of quasi-photosphere in the infrared for the modern Earth. It's a pretty crude approximation. So, but it's going to be radiating by the Stefan-Boltzmann law at sigma T to the 4. And then it passes through some optically thin gas. We'll call that a gray body slab. By gray, that word just means we have one absorption coefficient across all wavelengths. Okay, so that's a gray body. And this will absorb some fraction, absorptivity, which is this epsilon, which by Kirchhoff's law is equal to emissivity. So it absorbs some fraction of this flux coming up, and then it radiates itself at some temperature, which we call T skin. And it will transmit this. So we just do what's going out, that plus that makes 2 of those, versus what's coming in, which is what gets absorbed here. And then we solve for this skin temperature. And we get a simple expression, which is that the temperature of the skin is T effective divided by 2 to the power of a quarter. So if you do that for the Earth, 255 Kelvin, the skin temperature will come out as 214 Kelvin. And that's actually a pretty good estimate of the tropospheric temperature. It's within a few percent. And in fact, if you apply this to other rocky planets that you could imagine, the skin temperature would also be a pretty good estimation of a tropopore's temperature, or more specifically, if we're not considering something with a stratosphere, then it would really say just a classic radiative convective equilibrium profile. It's this temperature that it asymptotes to. right, in the upper atmosphere. Because this is optically thin up here, relatively transparent. And this is convection down here, radiation up here. So it's just dominated by this very simple concept of skin temperature. So we've now introduced those two ideas. No, this is a simple, I guess you could say, a two-layer approximation. Here is optically thick, and here is optically thin. And we're trying to figure out what, in an optically thin situation, this temperature will be in the upper atmosphere. And it's a valid approximation. Yes, so you'll just get more and more. It will just be an isothermal skin temperature like this if you do that same kind of thing. So now apply this in a thought experiment to climate. So let's imagine an idealized, rapidly rotating, airless planet initially. We assume that it's rapidly rotating so that temperature is spread, let's assume that it's isothermal. Okay? It has to be the same temperature everywhere. And this means that the surface temperature will be the effective temperature. Okay? Now let's add some gas around this body, and let's assume it's a non-greenhouse gas. So something like pure nitrogen crudely would approximate that. It's not strictly true because it's going to absorb something. And let's play God, and we'll say no convection, not allowed, only radiation. So we would have this surface would radiate at the effective temperature. In the upper atmosphere, or in the optically thin atmosphere, it would be absorbed, and you'd have basically a skin temperature in this very thin gas. But of course, this is completely unphysical. Why? Because near the warm surface, it's got to convect. So let's add convection, and then we get this. We'll have a convective profile. Remember, this is still not a greenhouse gas in this atmosphere, so our surface temperature is still pretty close to our effective temperature. But we now asymptote to our skin temperature, like this graph I drew here, which was meant to have Z on the y-axis, z-axis. So this is now really a very simple climate model, but would apply, crudely speaking, to a planet with an optically thin atmosphere. It wouldn't be too bad. But it's still unphysical because in reality, our planet is going to have some greenhouse gases. So we're still playing God, so let's take a spoon and we'll stir in some greenhouse gas into our atmosphere. So, and now we'll get diagram number 3. So what's going to happen is that just like the Earth, as we talked about the approximation, now the emission level shifts up. It's no longer emitting the effective temperature at the surface, but from some higher level. You can think of this as an infrared photosphere, if you want to put it in astronomical terms. But our surface temperature is now bigger than the effective temperature, but we still asymptote in the optically thin region of the atmosphere to the skin temperature, in this case. And that's basically what we're seeing is the greenhouse effect. So the greenhouse effect is just this difference, or you can think of it as this difference between the surface temperature and the effective temperature. A more physical way to think of it is the difference between the radiative fluxes, although that's more abstract. So in these simple climate thought experiments then, we've actually got something which is a pretty good approximation for how a 1D climate model works. We assume an average, a global average, and we can collapse that down to one temperature structure. And in this case, it doesn't have the added complexity of some shortwave absorber up here, which would create a stratosphere and a turnaround. And we're not really considering all the other things that could go on, such as thermospheres or mesospheres that I talked about in the previous lecture. We also can add our concept of optical depth in here. So what will be the optical? So the optical depth up here is 0, is how we're defining it, and it increases on the way down. So what is the optical depth here at this dashed line in the infrared? You're not allowed to answer, your faculty, students. So it's unity, approximately. So remember, this is our boundary where it sort of starts to become optically thin at this level. Strictly speaking, it's not going to be unity because there are slant paths, but that's a wrinkle. So up here it's 0 to the infrared. Down here it's unity, so this is roughly where the level of escape of those infrared photons. Down here at the surface, the optical depth will exceed unity. So on the Earth, for example, if you did a gray body approximation, the optical depth of the surface actually is not that big. It's about 2, something like that. But in the giant planets, if you looked at the gray body optical depth at, say, 1 bar, to compare with the Earth, you'd find something like a few, or maybe 5. I think Saturn has the biggest one, which is about 8. If you looked at the optical depth for Venus, it would be very large, hundreds at the surface in a gray body approximation. So this is, if we were to stir in more greenhouse gases, all that would happen this surface temperature would increase, it would shift this way, and our emission level would go up, right? Level of unity optical depth, because now we've got more optical depth down at the surface. And that basically is how a 1D climate model works, and is a reasonable approximation for how climate works as a whole. We can add realism to this 1D model. What we could do is put in different gas mixtures, pressure and temperature and wavelength dependent infrared absorption coefficients. So if you kept it simple, that would just be an absorptive atmosphere. Then you can do other things. You could add scattering to the model. But these models have a long history. So this is really, back in the 1960s for the Earth is when people really started to do the numerical models, and there was enough information. So in this case, what we're looking at here, here's the Earth. On this axis is temperature. This is pressure in millibars, 1,000 at the surface, or altitude here in kilometers. If you did a purely radiative model, you would overestimate the temperature at the surface, and you'd also overestimate, well, you wouldn't have the right estimate of the decline of temperature with altitude. Because in fact, this decline is sufficiently steep, the temperature is decreasing a lot with altitude, that it's very warm here relative to higher altitudes, and so convection should kick in. So it kicks in this dry case. So this is a dry adiabat, not considering moisture. If moisture is added, then the release of latent heat will change this from 9.8 Celsius per kilometers to, in this case, they've got 6.5. The global average is actually close to 6 if you look at data for the Earth. So this is from Marnaby and Strickler, which a lot of people, it's a very highly cited paper, put it that way, because they basically figured out how to do this for the Earth and how to do convective adjustment to adjust to this convective profile, and how to put in some estimates of what the effect of water vapor. One can go from the 1D case to the 3D case. So you can make your climate model more and more complex with adding bells and whistles. So I talked about scattering. You could add clouds. With 3D, you've now got dynamics, which we just heard about. But on a planet like the Earth, you've also got ocean dynamics. You've got ice sheet dynamics. And then you've got this stuff down here, which Van Leeuwenhoek discovered, the microbes who are sort of driving everything. Well, at least on the early Earth today, we have trees and vegetation that are also quite important. Even if you step up in this complexity, you're if you collapse everything back to the 1D, it will still be pretty close to your 1D radiative convective model if you've done that correctly, except clouds will obviously affect things around the planet quite substantially. Well, so it's obviously a global average, and so if you go to obviously certain times of day, you could have an inversion at low levels. If there's, say, smoke in the atmosphere, or if you're on the poles, you could have a very cold surface and a warm atmosphere, so you could have an inversion. Your scale height varies as a function of latitude, as was mentioned earlier, from about 17 kilometers at the equator to about 7 kilometers at the poles. So that's a big factor. Yes, yeah. Well, except when you get to the thermosphere, which is very variable with its temperature because of the variability of the sun in the short wavelengths in the EUV, and so that varies a lot, hugely daily in its temperature, and it responds very quickly. Temperature, there's much more inertia lower down. So let's have a look at sort of relative greenhouse effects on other bodies. One way to think about that is you could think of the fraction of the total flux reaching the surface due to thermal infrared from the atmosphere. So in other words, you've got the atmosphere here absorbing in the thermal infrared, and that's infrared coming down, which is warming the surface in addition to the solar flux that's coming in. If you look at that fraction, and I've ranked them, on Venus, basically, it receives such a small amount of solar flux that the infrared downward flux is dominating that heating virtually completely. On Titan, it's about 9/10, Earth, it's about 2/3, and Mars about 1/3. So this is one way of thinking about the relative magnitude of the greenhouse effects on these various bodies. But of course, if you look at this diagram, your balance here is what's coming down. The net solar flux plus the infrared down must equal the infrared flux up plus some convective flux. We can also see the greenhouse effect if we look at the Earth from orbit. So here we've got radiance in these units of watts per meter squared per steradian. This is in wave number units, but here's wavelength, which will make you feel happier, probably. Chemists like to use these. Physicists like to use these. On this diagram, this is actually a spectrum taking over North Africa. And what we see are various black body curves that are dashed. And then we see the actual curve from the Earth. And if the Earth were just a black body, this would, of course, be a smooth curve at the appropriate emission temperature. Instead, we have these bites out of it, the most prominent ones being CO2 and ozone. And those bites out of a smooth curve mean that something has to move up to compensate, which is really the greenhouse effect. So here we're seeing in this window a 320 Kelvin surface. So the photons here at this wavelength are going from the surface of the planet through basically an optically thin region of the spectrum, and we can see the surface directly. But elsewhere, we see cooler brightness temperatures, which means they're coming from higher up in the atmosphere. But this is effectively a visualization of the greenhouse effect. And we see a lot of water vapor bands out here, 20 microns, over here at these wavelengths, and methane here, 7.6 microns, ozone, 9.6 microns, CO2 band at 15 microns. Now you notice a little spike in the middle of the CO2 band. That tells you that some of the CO2 is radiating at a warmer temperature than 215 Kelvin here. 215 Kelvin, where's that going to be? It's going to be mostly at the tropopause level, roughly speaking, where it's finally, the photons from the warm troposphere are mostly emanating from that level. But a bit higher up in the stratosphere, there's still some CO2, and that's radiating at a higher temperature because the stratosphere is a thermal inversion. So this little spike here is a sign of a thermal inversion in this atmosphere. If you saw this on an exoplanet, if you had the resolution, doubtful, but if you did, you'd be able to see that. Now, you can be fooled because there's a spike here in the ozone, but that spike is actually not to do with the stratospheric inversion. It's to do with the band structure of the ozone. It just happens to look like that.
Why should it have to be at that particular wavelength, see at a different level of the atmosphere?
Good question. I think that's the middle of the band, which is going to be strongest and most absorbing. So it means that it only becomes optically thin at a higher altitude, in the most absorbing place. Whereas on the edges around here, it becomes optically thin lower down. Yeah. So the way to interpret this is with this little interpretive diagram. So you can think of the 215 emission, sigma t to the 4, happening at the tropopause at 15 microns, or at least here, not in the middle, which is somewhat higher. You can think of the 11 micron here doing a sigma t to the 4 at the surface temperature. This is in Africa, where it's hot. And if we go over here to the 20 micron bands of water, where are we? Here, 20 microns. Then what's this black body temperature? I've estimated as 265 Kelvin. So your sigma t to the 4 is coming here. Where would 265 Kelvin be? What altitude? Based on information I gave you in previous slides and a little bit of arithmetic. So 6 Kelvin per kilometer. Yeah, so it's going to be in the middle troposphere, roughly speaking. So this is typical of, yeah, it's not too far off that, maybe a bit lower. This, of course, raises the question of can we deduce a rocky planet's surface temperature using spectrum from afar, which is a very important question for studying rocky exoplanets, because it's the surface temperature, remember, which tells us whether liquid water might be stable, and therefore whether that planet might not just be habitable in reality, but might be inhabited if we think the Earth is typical where you find liquid water. All right, so this lecture is on the subject of climate and radiation. Again, my focus is rocky planets mainly. So what I'm going to talk about is the outline, some basic climate physics. So I'll start with some simple climate thought experiments. Then I'll talk about some molecular issues of radiation, absorption and emission. And then finally, I'll talk about climate stability, so long-term feedbacks that maintain a state. Body curves, if you calculate the total flux, it's just the Stefan-Boltzmann law for a black body. So that's where we start. And an atmospheric skin temperature is, so imagine your planet then has to radiate at an effective temperature for the Earth, that's 255 Kelvin. It doesn't do that from the surface because the surface temperature of the Earth is about 15 degrees Celsius on average. So instead it does it from some average level. Is familiar with black bodies for the Sun and say for the Earth, and for the emission of the Earth being about peaked at 10 microns in the visible. For solar, this is scaled by a factor, and basically the effective temperature of the Earth here is 255 Kelvin, which is equivalent to the basically bouncing solar radiation without going thermal infrared. And these black are on its surface, so having a temperature and pressure regime where that's possible. And of course, this defines the habitable zone around other stars. So to gain insight into climate, let's consider some simple thought experiments. We'll start with the basics. the emission temperature of a planet, and something which you may not have come across, but the skin temperature of an optically thin upper atmosphere. I'm assuming everybody able and habitable climate on the Earth, and then also a particular case when things go wrong, which is the worst case of instability probably, which is a runaway greenhouse, which illustrates some of the issues of radiation that I'll talk about earlier. So, first of all then, some basic climate physics. Why do we care? We care for Earth-like exoplanets basically because of the issue of habitability, which conventionally defined means liquid water